Hi, today we're going to talk about section 8.4 mutually exclusive events. This is on pages 382 and 383 of Abeka pre-algebra. So let's get right into it. The lesson starts out immediately talking about George, and he's playing a game, and he has to roll a dice and get either less than 2 or greater than 4 to be able to land on a safe spot on the board game. All right, so we have these dice right here. And I've color-coded the less than 2 event and then the greater than 4 events, blue and then red. So these are mutually exclusive events. Hopefully you see that if you roll a 1, you didn't roll any other number. To roll one number means you have excluded all the others. They're mutually exclusive. So that's this term mutually exclusive is one that's important to understand. These are events that cannot occur at the same time. The example that I just gave you about George needing to roll a number less than 2 or greater than 4 is also compound events. It's 2 or more separate events that could occur. He could roll a 1, he could roll a 5, or he could roll a 6. So to find out the compound probability of compound events, you simply add up the individual probabilities of each of those scenarios of those outcomes. So the probability of rolling a 1 is 1 out of 6. And the probability of rolling greater than 4 is, well, you could roll a 5 or you could roll a 2. So there are 2 possible outcomes. 2 over 6. 2 out of 6. And you add those up and you get 3/6, which reduces to 1/2. And a lot of times they ask you to put the probability in as a fraction, a decimal, and a percent. So remember the fraction will always be between 0. The fraction and the decimal number will always be between 0 and 1. All right, so it's going to be greater than or equal to 0. Probability will be greater than or equal to 0 and less than or equal to 1. Wow, I wrote that wrong. Probability will be greater than or equal to 0. Sorry about that. Less than or equal to 1. I really have trouble talking and writing. All right. So 1/2 is in between 0 and 1. Then that equals 0.5. And then that equals 50%. Remember, multiply by 100 to get percentage. All right, so we're going to look at a quick example. Mr. Todd's 8th grade class was asked which subject they liked best. Of the 36 students, 18 preferred math, 4 preferred history, 8 preferred science, and 6 preferred English. All right, and then it's going to ask us to express it as a fraction, a decimal, and a whole percent. Decimal to the nearest hundredth. Okay, so what is the probability, looking at A here, what is the probability of randomly selecting a student whose favorite subject was either math or English? So these are mutually exclusive events. These students had to pick a favorite. They didn't get, have a tie for history and science or whatever it might be. So we have 36. We know out of 36. So we can go ahead and make our denominator 36. But the number of people, the number of students that like math was 18. And then the number of students that liked English was 6. You add those compound events to get the compound probability. And it is 24 out of 36, which reduces to 2/3, which is about 0.67, or 67%. Then you're asked, what is the probability of randomly selecting a student, excuse me, a student whose favorite subject is either science, history, or English? So the number of students that like science is 8 out of 36. The number of students that preferred history was 4 out of 36. And then finally, English was 6 out of 36. So we have these mutually exclusive events, and we're going to compound the probability, get our compound probability, and we get 18 out of 36, which reduces to 1/2, or 0.5. Remember to express your answer and all the different possibilities that they're wanting, or 50%. All right, so we have one final little thing to look at. If you're reading news articles or magazines, you are not going to usually see 1/2s or 0.5s. You'll see 50%. You'll see things, these probabilities expressed as percents. So you can still compound the probabilities and find compound probabilities as long as the events are mutually exclusive. So we are told that vacation transportation, people either used car or plane or RV or train or some other mode of transportation, but they are mutually exclusive. The person who used the car only used the car to get to their destination. Oh, sorry, my mouse is acting funky again. Where'd it go? Okay, there we are. Okay. So these are mutually exclusive events. So we can compound them fairly easily. The probability of car or plane would simply be 59% plus 33%. Super, super, super easy. But what if they asked how many people didn't travel by plane, or what is the probability that people did not travel by plane? That is looking at the complement to the plane, the probability of the plane's complement, okay? And this is a review from section 8.1, so you can go back and watch that video if you need that review. But real quickly, the complement equals the probability of the complement, or the probability of the event's complement, equals 1 minus the probability of the event. Okay, so you can say that the probability of the plane complement is done one of two ways. I'm going to walk it out both ways because that's what the book does. I could say 100%, because our numbers up here are expressed in percent, so I need to convert my 1 to a percent. So 100% minus 33% equals 67%. But if the thought of subtraction horrifies you, you could also do the probability of the complement to the plane, and quite honestly, I'm not positive that you'd read it that way, complement of the plane, but I do know that we're talking about the complement. You could add up all the other probabilities. So there's 59% for the car, 5% for the RV. We're skipping plane because we're trying to find the complement to the plane. 2% for the train, and 1% for the other, and lo and behold, you also get 67%. You can do it either way. All right, that is it for this lesson. Good luck with your homework.